everyone. Good morning, everyone. I'm Tim Smith, Associate Provost of the College, and it's my great pleasure to welcome you all here today to our Provost Forum, this time featuring Dr. Laura Stultz. Before we begin the usual public service announcements, we do ask you please to silence or deaden your phones. And then particularly those folks who are sitting towards the back. We've got Gina back there who is videotaping this for posterity. We don't really necessarily need your additional commentary on that recording. So if you're sitting towards the back close to that recording, we do ask particularly that you don't talk during the presentation. Now to our speaker today, Dr. Laura Stultz, Professor of Chemistry, joined the BSc faculty in 1997. She received a BA from Oberlin College and a PhD from the University of North Carolina at Chapel Hill. Dr. Stultz's research interests have included, and don't ask me to explain these, bioinorganic chemistry, coordination chemistry, does that sound right? Electron transfer reactions of transition metals, and metal-containing anti-cancer drugs. Her talk today is entitled Understanding the Mechanism of an Anti-Cancer Drug Through Interdisciplinary Collaboration. So very liberal artsy talk today. Please help me welcome to the stage Dr. Laura Stultz.
Get away from the podium and still be doing like. Thank you so much for being here today, and thank you, Tim. And I've got a lot more thanks, but those will all go at the end. So I'm just going to jump right in. And all the things you talked about, Tim, are what we're going to mention today. So. All right, so let's start with the periodic table. That's where it always starts, right? Any chemistry class you've ever had in middle school and beyond, you probably saw the periodic table. I may not know exactly about it, but this is actually 2019 is the year of the periodic table by the American Chemical Society. I know you've been celebrating since January. We still have many more months to go. And the periodic table is celebrating its 150th anniversary this year. So that's a big deal. It was discovered or arranged or organized in the 1870s by Mendeleev. You may have heard of him. Maybe not. But at the time, there were only 65 elements. And what he was able to do was arrange those elements by their masses, by their properties, and come up with a structure. And the real advantage of that structure was that he was able then to predict which elements were missing. We have 118 today, and some of these are very recent, but he was able to see holes in the structure and predict what elements would be there and their properties, and later it was a good predicting tool for what elements we were missing. Now, if you're an organic chemist, like Dr. Schiller, you spend a lot of your time up in this region of the periodic table. Carbon, nitrogen, oxygen, hydrogen, and there's enough there for many lifetimes of chemists to study that to infinity, right? There's so many, it's a very rich area of chemistry. But that leaves the rest of the periodic table for inorganic chemists like myself. And because there's a lot of elements there and a lot of things to study, I've limited my focus to these transition metals that you mentioned in the coordination chemistry of these metals here in the middle. So these are metals you've heard of: copper, silver, gold, platinum, iron, vanadium, I don't know the vanadium, but titanium, you've probably heard of that. Those are all elements that you're probably somewhat familiar with. And when I tell people I study metals, they typically think I'm studying sort of these shiny things, right? When you think about metal, you think of shiny copper, or this is platinum, this is mercury, which is a liquid. But in reality, I don't study this kind of metal either. Sometimes it's nice to have some iron in the lab. What I actually study are really metal ions. So what I mean by metal ion is that the metal has a positive charge. It's lost electrons, and it has these positive charges. So we have manganese, iron, cobalt, nickel, copper. And notice all the beautiful colors, right? So when you have these iron complexes or these iron charged species, or these metal charged species, I should say, they give you beautiful colors. And the color depends on the charge of the metal. It depends on the identity of the metal, which means these are all different metals. It also depends on the environment around the metal. So we can learn a lot from these colors, and I'll be talking more about that in a minute. Back to the periodic table. So my focus is on my favorite element. Everyone know what my favorite element is? Ruthenium, right? Ruthenium badge here, right? Everyone should have a favorite element, and mine is ruthenium. And you might ask, why ruthenium? Well, ruthenium is right here in the center of the periodic table. So the center of the transition metals. And being in the center is a good place to be. The ones at the top here, they tend to be overly reactive, and they're difficult to work with sometimes. They tend to oxidize very easily, corrode, form some iron, rust, things like that. You get a lot of different compounds here, and it gets to be a little tricky to work with them. The ones on the bottom here are very sluggish. They don't like to do much chemistry at all. You have to really boost them with a lot of charge to get them to do anything interesting. So in the middle, you get sort of nice, easy chemistry, easy to do. Ruthenium in particular is not very air sensitive. Some of its neighbors, rhodium, palladium, can be very air sensitive. You can work with it very readily. It's not super expensive, like the gold and silver counterparts you may be familiar with. And so it's a very nice element to work with in a lot of ways. And iron is right above it. It shares a lot of properties with iron, and I'll be talking more about that in a minute. Okay, so ruthenium. Just so you know, I'm not the only person in the universe celebrating or studying ruthenium. There are a lot of different things related to ruthenium, a lot of research that I'll just briefly mention. In 2005, the Nobel Prize went to one of the recipients, was Robert Groves, and he developed a Groves catalyst. Actually, this is just one of them. There's a series of catalysts that he's developed. And those catalysts are able to take reactions with double bonds and rearrange those double bonds in different ways. It's called olefin metaxis. And that in itself may not sound too exciting, but that's really the basis that's used for developing polymers or plastics or different materials, all kinds of organic reactions, including developing pharmaceuticals, biomaterials. They all need to have this very controlled chemistry, and his catalysts help make that happen. The other star in the world of ruthenium is this compound called rutris-vipi. It's ruthenium in the middle, and these little things on the outside are called vipi, bipyridine. And what rutris-vipi can do is, when you shine light on it, the electron from the ruthenium gets moved to the ring, and this, we call it charge-separated state, it has a lifetime of hundreds of nanoseconds, which is a long time for chemists, for these sorts of things to exist in this state. And because it's in this excited state for a significant period of time, you can do chemical reactions with it. And so basically why this is so important is you can use light and you can convert it into chemical energy. And what else does that? What else converts light into chemical energy? Plants. Plants do that. And one of the holy grails of chemistry is trying to figure out how to do what plants do without even thinking about it. Another side of that is looking at what's called water oxidation. Plants do that as well. Plants are able to convert water into oxygen. It's very difficult to do that chemically, and so there's a series of ruthenium dimers that can effectively do that in some scale. They're trying to improve these and ideally link these two things so you can use the light to do both of the chemistry. Now, I don't do any of this, but just wanted you to be aware of it. What I do instead is I work with metal-containing anti-cancer drugs. And in particular, ruthenium is ideal for that. One reason it's ideal for that is because, as I mentioned earlier, ruthenium is very similar to iron. And your body uses iron in lots of different capacities. And in many ways, your body can be tricked into thinking that ruthenium acts like iron, and it can use it for different uptake pathways. So this particular drug, which I call KP1019, was first synthesized by a chemist in Austria named Kepler, Bernard Kepler, that's where the KP comes from. And there are other metal-containing anti-cancer drugs, mostly that use platinum, but the platinum drugs tend to have a lot of side effects, and those are problematic. And they also, some cancers are developing a resistance to the platinum. So alternatives are always welcome. So there have been studies with KP1019, not by our group, but by faculty or researchers who've been looking at specifically studying ruthenium compounds like this with cancer cells. And they have found that you can take a tumor in a rat and you can treat it with KP1019, and it seems to cause remission of the tumors and lowers its volume, which is a good thing. There's also been a very limited human trial. Really very few patients, but in that very limited trial, it did show to be effective in stabilizing patients. And the other main thing is that it wasn't very toxic, which is a good thing. So let's talk a little bit more about the fundamental chemistry and the properties of KP1019 and what we're looking at to understand that better. So here's my molecule again, KP1019. It's not really my molecule, but I'll take it. It's one that I work with and my students make. And it starts out with a +3 charge. Remember, the charges are really important in the activity of these transition metals. So it has a +3 charge here. And it's believed that in the +3 state, the drug is effectively inactive. It doesn't do much. And so it gets activated when it gets reduced to when it gets reduced to a +2 charge. Now, when you have a +2 charge, the things that surround the metal, these are called ligands. The ligands that surround the metal have a slightly less attraction, and so you can exchange these ligands for other things. In this case, I've shown water, but it may be that when this exchange happens, the ruthenium is able to bind to biological molecules in the cell, things like DNA or proteins or RNA, and that could be the cause of its activity. So part of the chemistry that I'm focusing on is this reduction reaction. It's really important that we understand under what conditions this reaction takes place, this activation or this reduction of the metal center, and then what happens after that reduction takes place. So I'm going to show you some data, but don't be scared by it. I'll try to explain it best I can, and I think if you just focus on the parts that I'm talking about, it won't be that bad. So the first way that we study these oxidation and reduction reactions, reduction is the reduction of the charge from ruthenium-3 to ruthenium-2. The oxidation would be the opposite of that, the ruthenium-2 going to ruthenium-3. We can use a technique called electrochemistry. And in this electroanalytical technique, we basically take our sample and we change the environment around the molecules to make it more reducible. So as we do that, that's this axis. So if we move in this direction, we're making the reaction environment more reducing, more favorable for a reduction to happen. If we move this way, we're making it more favorable for an oxidation to happen. And what we're measuring is the current, or the flow of electrons. So as we move through this different potential circle, what we see is that as we go to a more reducing environment, we see a flow of electrons right here, this peak. And that peak corresponds to the ruthenium-3 metal getting reduced to a ruthenium-2. That's the important reaction that happens. It activates the drug and potentially makes it be biologically active and work as an anti-cancer agent. So then, as we come back around, we can cycle around, and we can see on the other side, we can see that the ruthenium-2 species we just generated can get reoxidized back to ruthenium-3, and that's what this peak is here. So these peaks are what we're really studying. We're looking at the reduction, ruthenium-3 to 2, and the oxidation of the ruthenium-2 back to ruthenium-3. And where this peak is very important for the activity of the drug. If this peak were moved a little bit over in this direction, that would mean that the compound would stay in the ruthenium-3 state and therefore not work as well, not get activated. If it happened to move a little bit more in this direction, that would mean it would get reduced too readily and it would be activated maybe before the target of the cancer cell. And that wouldn't be good either. So this region right here is where biologically reduction takes place in the cell. And by optimizing where these reactions take place, we can therefore make it so that potentially the reduction occurs in the environment of cancer cells. The other thing we can use this for is to determine determine what the oxidation state of our compound is. So as I showed you recently, we have the ruthenium-3 getting reduced to ruthenium-2. We did a similar reaction where we took the KP1019, but we reduced it. We used a reducing agent. So a reducing agent is a chemical which causes the reduction to take place. And when we do that, we see that that peak here has disappeared. We still have the corresponding oxidation peak, but we don't have the reduction. And that tells us that our compound is reduced. It's in ruthenium-2 form. And that's helpful when we're doing our analysis. Now the other thing that we like to do is look at color changes. And my students set up this reaction in the lab. So they set up the KP1019 control, and then they added different reducing agents to it. And we just sat it on a piece of paper, and over time, we looked at how the colors changed. And you can see that when we add, these are all different reducing agents. We add different reducing agents, we got different colors. So that means that different chemistry is going on for those in those different reactions. And then over time, we can see changes happening as well. So this is important because these color changes tell us that something's going on, right? And that's important, and it's a nice visual to tell us that we need to be paying attention to these reactions. Now, where does the color come from? We can't just look at color changes. We need to somehow be able to quantify that. And the way we do that is what's called visible spectroscopy. So what's happening here is we're shining light on these compounds. This is white light. Remember, white light's made up of red, orange, yellow, blue, and indigo, violet, right? All the different wavelengths of light. We shine white light on our solutions. We have a solution with a metal complex. And the energy from that light, some of that energy is being used to take an electron and move it to a higher state. And in this particular example that I'm showing, it's the green and the yellow light that's being used to promote these electrons. So what happens is that this light is absorbed by the molecules in the solution, and then the other wavelengths of light, the reds and the oranges and the blues and the purples, pass through. And so that's what we see. Our eye sees the light that passes through, that's transmitted. But the light that's really doing the work here is the one that's absorbed. Right? In this case, it's the yellow and green. So we can measure an absorption spectrum. If you look down here, these are the different visible light spectrum, starting with red going to purple. And we can see that this peak corresponds to the area of the green and the yellow, right, where the light's being absorbed. So we're going to be looking at things like this, but what we're seeing in the lab are these color changes due to the light that's actually transmitted. So let's look at the absorption spectrum for KP1019. And KP1019 is kind of a golden amber color. It's got oranges and yellows and a little bit of reds in there. And the reason why it's colored is because we're absorbing light up in this region where the blues and the purples would be. And so the spectrum that we're going to be looking at is this one. Right? This blue line is what we start out with, and over time we see a little bit of change due to changes in the electronic environment around the metal center. Now when we add a reducing agent, in this case, the reducing agent that we're using is ascorbic acid. You've probably heard of ascorbic acid. It's in vitamin C, right? And it's a reducing agent. And when we add the reducing agent to the KP1019, we see the color turns a little greener. And that's because now we are not absorbing as much light in this region. And this is our original KP1019, and this peak here is the reduced piece. And this is what we've seen. We've been reducing KP1019 for years. This is a sort of signature that we saw for these kind of reactions. Well, one day, we used a different reducing agent. The reducing agent was called glutathione. And once again, we started out with the KP1019 peak, but then we saw this. We'd never seen that. We'd never seen this kind of increase in absorbance in this region. And I've never seen it in the literature on these compounds as well. It's really unusual for these kind of reduction reactions to see this. So we tried to reproduce this reaction, and some we were able to sometimes and not others. It was actually quite confusing. So here's an example of a study that we did. So we took our reducing agent, the glutathione, and when we just use a twofold excess, that means double glutathione to the KP1019, we start out with the KP1019 and we see the same sort of changes that we saw with the ascorbic acid. We increase the GSH to a factor of 10. We see a little bit of shifting of that, but really effectively the same type of spectrum that we've seen before. But then when we go to a 20-fold excess of GSH, so 20 times GSH for our metal complex, we begin to see this happen. And so our first initial response was, well, this must be due to the GSH. We're not seeing this with any other type of reducing agent. The GSH must be doing something. Maybe it's reacting with the metal. We know the metal in its reducible state can react with biomolecules. GSH is an important biomolecule. It's a reducing agent that's found in cells, and cancer cells have a higher concentration of this reducing agent. So maybe there's something going on with that. Another weird piece of data we saw was that both of these runs, this is what I just showed you, have a 20-fold excess of the glutathione or the GSH. In this case, as I showed you, we have this absorbance. But in this example, we just have half as much KP1019, still the same 20-fold excess of GSH, but we don't see that peak again. And that's part of the reason why we were seeing it sometimes and not others. This happened to be a coincidence that we went to a lower concentration. I don't know exactly why we were doing it at the time, but it wasn't something we had really intended to do. And so, once again, this has been really puzzling for us. So, what we started to do next was to combine the two techniques that we've been looking at. So, I showed you the electrochemistry where we can look at the peaks that tell us about the oxidation state of the metal. And what we're able to do, this is a technique called spectroelectrochemistry. And Dr. Dorman shared with us his setup, his experimental setup, so thank you for that. And I've had 2 or 3 different students work on this, sometimes unsuccessfully, but recently Todd Anthony Pellegrini worked on this summer and got me some great data on this that I'm sharing with you. So what we're able to do in spectroelectrochemistry is instead of just scanning the whole spectrum, the whole range of potentials like I showed you earlier, we're going to stop at one potential and sort of take a picture, right? So in this case, we're going to be able to measure the absorbance spectra at a particular potential. So we did it first at 100 millivolts. This was our KP1019, and then when we held the potential right here, we did see a reduction take place, like I showed you with ascorbic acid. Moved up a little bit further, right? We held it here, kind of took a picture of the spectrum, and we see a little bit of change. So here's what I showed you before. We have this new peak sort of coming in here. And then when we went past the peak and started collecting data, we see this again. Right? By now you know this is something I'm kind of excited about seeing, right? And my students were excited. They came to my lab, we found it, it's so new. And what's so unusual about this is there's no glutathione. We spent years thinking that the glutathione, which was causing this peak, but in this particular reaction, we don't have any reducing agent. We're just reducing it by changing the potential. So that tells us that our original hypothesis is wrong, and that's fine. But now we want to really know, when can we see this peak and when do we not see it? So another technique that my students have used is NMR, nuclear magnetic resonance spectroscopy. I'm not going to go into all the details of that technique. But what you need to know is that what we're looking at are these hydrogens, you can't even see them shown here, but the hydrogens that are bound to these rings. And they have a distinct signature in this technique. So when we have the ruthenium-2 form, when we have the ruthenium-2 form, when we have it as ruthenium-3 in the oxidized form, we don't see any peaks here. The ruthenium-3 has an electron, an extra electron that interferes with the NMR spectrum, so we don't see any peaks at all. When we reduce the ruthenium to the ruthenium-2 state, we begin to see the peaks that correspond to the hydrogens on these rings. And over time, we can see changes in those peaks. So notice here, I had arrows, but I'll just point them out. So a new peak here, here, here. All these peaks, in this case it shifted a little bit to the right, here it shifts a little bit to the left. And that tells us that there's something going on in the environment around these rings. Probably what's happening is we're changing maybe one of these chloral ligands for something, and that gives us a slightly different environment, which causes the peaks to shift a little bit. When we use glutathione for that, right, our other reducing agent, once again, we don't see anything in the oxidized state, the ruthenium-3 state. When we reduce it, we see the peaks again, but now we see a different peak. Last time we saw a peak on this side, but now we see a peak on this side. And notice that we have new peaks, but they're on the other side. So that tells us that there's something else being formed. It's not the part that we saw with ascorbic acid, but there's another reduction product being formed. Over time, we go back to seeing this peak we just saw, and then the peak that we originally saw with ascorbic acid. So it means there's an intermediate state here that we're getting with glutathione, but we're not getting with the other. So my students, after my sabbatical, I came back with lots of questions, and I had two students, Anthony Pellegrini and Daryl Dunbar, and they spent the entire summer slogging through doing lots of different exciting reactions, right? Where they very carefully looked at all the different reaction conditions that we typically use, all the different instruments we typically use, and try to categorize when do we see this new species, when do we not see it, under what conditions can it be found. I'm not going to go through all of that, but what we have learned in this process is that what happens in this reduction reaction depends on the reducing agent. We've seen that using different reducing agents. It depends on the reduction potential, so how reducing environment we're seeing around the cell. Depends on the concentration of the reducing agent. Right? We saw that with the GSH. Depends on the concentration of the metal complex. We've also demonstrated the temperature, so it depends on the temperature and it depends on the pH. So these are all factors that we've been trying to categorize to be able to figure out what the new reduction species is that hasn't been reported before. So we have lots of questions left. The first one is, this new reduced species that we're able to characterize, does it react with biomolecules, right? Is it the active form that's being used in cells? We don't know that. So right now we're looking at reacting the different reduced species that we now know how to generate with different biomolecules like DNA. The other thing we want to know is how stable is this new reduced species? Is it something that might exist in biological conditions? So we're going to try to play around with the stability. Does it last for a long time? Is it just something short-lived? We have some good ideas about that, but we're trying to understand that a little bit more. And finally, what is the chemical structure? I have some hypotheses about this. I don't know if I'm willing to share at this point or without having to require a lot of chemistry. But really, what is this different species? It has a very different spectrum than what we've seen before, and that means that it must have a different structure. We want to understand better what that is. So I'm going to take you back where this all started 15 years ago. And 15 years ago, David Shedler got a grant, Dr. Shedler in organic chemistry, and that grant was from the Merck pharmaceutical company, and they were funding collaborations between biologists and chemists, mostly. And so at that time, I was just studying my KP-1019, all by myself. And Pam Hansen, Dr. Hansen on the second floor was studying yeast. And these yeast are a wonderful model organism for cancer cells. And so once we had this grant, we're like, hey, I do anti-cancer drugs, you do model organisms for cancer, why don't we become friends and do more chemistry together? So we did that. And we worked together for 15 years on these sorts of projects. And after doing that for several years, we got a grant from the National Science Foundation to actually integrate this research into our courses. So the classes I teach are chemical principles and inorganic chemistry. She, at that time, taught an honors cell molecular biology class, and she's taught a variety of 300-level biology classes where we do this sort of work. And what we've been doing is making what are called course-based undergraduate research experiences. So we've been taking part of our labs in these courses and adding the chemistry of KP-1019 and having our students participate in this process. And notice, these are first semester freshmen that are doing this. So So that's pretty impressive, and these are usually second semester freshmen that we're working with. So we're taking students really early in their career and getting them started and thinking about KP 119, because what else would you want to do, right? And so let me show you how this dynamic has worked over the years. So in the cell and molecular biology class, students were reading an article that showed that NAC, which is a reducing agent, reduced the bioactivity of KP 1019. So the students in the biology class did a study where they looked at other reducing agents. In this case, they looked at GSH, or glutathione, the one that I've been talking about. And they found that glutathione does lower the bioactivity of KP 1019 in yeast. So then, that result went to my inorganic chemistry students in the 300 level course, and they studied further the GSH, having seen some results in the biology, and they were the first ones to observe this new peak that we saw. At that time, they didn't really have a good quantification of it, but they saw that there was a reduction in reaction that occurred between GSH and KP 119. Another example, students in the biology class were reading about melatonin. Melatonin has been found to potentially have some anti-cancer properties. And so the students in the biology class did some studies with melatonin. They added melatonin to the yeast media, and they studied that. They found that the melatonin did in fact help the KP 1019 in inhibiting the growth of the yeast. So it went to my chemistry students. The chemistry students in the 100 level class studied melatonin, but they didn't really see anything happen. It was exactly the same. So we didn't see any evidence of a chemical reaction between melatonin and KP 1019. So back to the biology students, we're playing ping pong, right? Taking information back and forth. The biology students went back, and they said, okay, melatonin didn't do anything, let's try serotonin. It's another biological species. And they found that serotonin did in fact also increase the toxicity of KP 1019. But another important observation that Dr. Hansen made, and she noticed this because she's been working with me for a while, she saw color change, right? So she saw that when you use high concentrations of KP 119, we see this really extraordinary blue color, which we've never seen before in these kind of complexes. So I was too excited about this to actually wait for my class. So that summer, I had some students work on this. A student named Russell Day. He did extensive work looking at serotonin and KP 119. And he found the blue color was due to an absorbance in low energy. And we've been continuing to study this. Christian worked on it for a senior project. I've had other students over the years work on this as well. So, once again, it's a whole other story. I'm not going to go into all the chemistry of that. I think I've given you enough chemistry so far for one day. But there's a whole other area of research that came from this class, right? Came from 100 local biology students doing an experiment and seeing an interesting result. So this has really been a wonderful opportunity for me as a researcher to have for two reasons. One, my students get trained in class how to do these techniques. So when they come to become research students, they already know a lot of the underlying chemistry. But also it lets me share my passion for transition mineral chemistry and actually authentic research with students as early as their first semester in their freshman year. And that's very important. It's important to me as an educator. I hope the students get a lot out of that. And the way that we share data between the classes is we have what's called a KP 1019 wiki. You've probably heard of Wikipedia before, right? Where you can find all sorts of information about anything. But we have a wiki devoted to KP 1019. And that wiki, each semester, the students from the classes, they share their results on the wiki. So this main menu has all the different classes that have studied KP 1019 over the years. It's a lot. It doesn't even include all of them. And then each student in their project that they're doing, it could be in their 100 level course or their 300 level course, make a wiki page where they describe their experiment, what they found, what the results were, how they did the experiment, and that gets posted on the wiki. So when my 300 level inorganic students next week start doing their independent projects on KB 1019, I think I see you all paying attention, right? They're going to go to the wiki and they are going to look at what other students have done and look for promising leads of experiments that may have been done in a biology class or a 100 level chemistry class, and to be able to apply that to their 300 level research. And so it's also a good example of how students communicate with each other. So when students are doing these experiments and writing up these wiki posts, they know that someone later who may know who they are is going to read this, right? So they kind of make a little more effort than it's just me reading. So all of this work happened because I had students working with me. I didn't do it all by myself. I wish I could say I did, but it's all more fun working with students. And I've had, in the past few years, several student researchers who have worked with me for multiple terms. You see how each one of these represents an academic term when they've done research with me. And some of them, after taking the 100 level chemistry course or biology class, have actually done an intern with me. So my 3 seniors this year, Anthony, Marilyn, and Vina, they all started back in 16 in an intern class doing KP 1019 research, building on the work they had done in their freshman class, first semester freshman class. And Marilyn just kept working for them, right? And they did as well, right? And I had this student, Ante Rivik, you may know. He worked for 8 different terms with me on different parts of this chemistry. And because they do all this work, they get to go to national meetings or regional meetings. So here are my students at meetings presenting their research, and that's always fun to show them that. So I talked about Anthony and Marilyn, and Vina, who's doing the serotonin work. I mentioned Ante, who did everything over his 4 years here. Jake Martin and J.R. Guyton, they did a lot of their work 2 years ago, especially on the glutathione, and Jake made the first attempts on the spectral electrochemistry where we saw that first result. Devin looked at nanoparticles. Devin Patel, he did work with nanoparticles in KP 1019. He worked with Russell Day and Kyle Wilty, who are both in medical school now, and they worked for multiple terms as well. And Sydney Middleton was one of the earliest ones that worked on this collaboration. She actually did some of the work in helping to develop it to make it course-based. And she's just finishing medical school at UAB right now. So, once again, thank you to all of my students. I couldn't have done it without you. You've been really pivotal to making this happen. And it's not just that they do the grunt work, although they do that. They also come to me with great ideas. They would sit in my office on Friday afternoons. They would talk to me about the results. We would ask questions. They would help each other out. And we would have this real collaboration between the students and me that I really treasured. So thank you very much for that. And once again, none of this could be done without collaborators. Pam Hansen, who I've worked with, as I said, for over 15 years, this couldn't have happened without her input. And recently, 3 of her students have looked at these reduction reactions: Abby Spencer, Bella Elodie, and Josh Wild, who have been working with me this year and last year on that. Kate Hayden, one of my new collaborators. She and her students are looking at how KP1019 and DNA interact. And so Donnie, Abigail, Sue, Jackson, and Amanda are all working with her on this project. So more KP1019. Jim Mobley is my collaborator at UAB. He works with the Comprehensive Cancer Center, and I did my last sabbatical with him. And once again, I need to acknowledge the students in my classes. I see you there as well, right? The students in chemical principles and inorganic chemistry. They, I'm able to, by working with them, get a lot of great leads. They can try 15 different reactions in one afternoon, and then we can see what is promising to move forward to the next step. So even a negative result, which sometimes are not heralded, they can often help steer us in the right direction of what we want to do. So I'm very thankful for all of them. This work was mostly done on my sabbatical last spring. Sabbaticals were really critical in helping us maintain our scholarship and allow us to focus. I had years and years of student data that I had to kind of sift through and figure out what was good, what was not good, where to focus my research. Also writing up some of this work, and which we have it published soon, I hope. And so when I'm on the sabbatical, these are funded by the Provost, Associate Provost. And the Faculty Development Committee approves these, so I want to thank those individuals for for supporting the sabbatical program. And whenever you're on sabbatical, your colleagues have to step it up and fill in for what you're not there for. And so my department has always been very supportive of chemistry and physics. But in particular, on the third floor, Dr. Stanton, Dr. Dorman, Dr. Schindler, E.C. Delgado, who would exist without her, and Dr. South has joined us. It's been a wonderful collaborative environment, and I'm looking forward to continuing to work with them on all sorts of projects, joint collaborations as well. And I want to thank you. I kind of zoomed through the chemistry part. I wanted to get to the student part, but I'm more than happy to answer any questions, chemical or otherwise. I told you guys had a question. Yes?
So going back a few slides to some of the graphs that you had laid out.
To the what?
Going back a few slides to some of the graphs that you had laid
Yeah.
out versus like I think the different concentrations of K1
Yeah.
and 1.9 and things like that.
That's not the quickest way to do this. Okay.
Yeah. Going back a little bit further. Yeah. Okay. One more right there. So I noticed that there was kind of like an intersection point between like the 2-fold GSH, like down towards here, versus the 20-fold where it moves up. And I know that's probably not pertinent to your research or not. But I wanted to know, is there something significant going on there in the 2-fold versus the 20-fold, or?
So certainly there's a lot of different chemistry going on there, right? You can tell that. But this point that you're talking about right here, right, that's called an isospecific point. So, or, that's where, when you see points like this that are clean, like here, that generally means you're going from one species to another, right? So it doesn't always mean that, but it often means that your reaction, one species, this is where the two different species that you're making have the same absorbance. And if you have lots of species, it's less likely to have those because the likelihood of 3 or more having the same absorbance at that particular wavelength is unusual. So you can see down here, we don't really have one. We have a little point here, right, where you're seeing a transition. And the fact that that's different, that tells us we have different products that are being formed. So it's really just as simple as that.
I'm assuming these were performed in phosphate buffer?
These were all in aqueous phosphate buffer, yeah.
Is it possible to have very consistency with other buffers?
Well, we've used different pHs. So we've used KHP buffer at pH 4 that we use. Yeah. I'm looking at my students, right? So yeah, we did a lot of the chemistry at pH 4 because that's where yeast are happy, right? And we want to make our yeast happy. So so we have to make sure that the chemistry that we're seeing can work in that environment. And for that we've used both buffered and unbuffered solutions in that environment. The chemistry is different, which makes it more complicated. But yeah, most of the work that I've showed you here is all in pH 7. But yeah, you can look at different pHs and you get different chemistry, and that's a whole other variable that we have to continue to look at. Yeah, Alex.
I recall earlier the conversation I had with you and developed from that slide. That's the said that the chemical or KQ119 exhibited the peak with 10-fold glutathione. And
it looks very similar to the 10-fold. That's correct.
yes. But that doesn't really match my understanding of how that works with the voltage to which that also produces this result.
Right. So you're bringing up a good point. And one is that, well, the voltage, we don't have any glutathione. We don't have any reducing agent at all. We're just manually reducing. So it's another way to get that. And once we got this, and we knew it wasn't from glutathione anymore, we went looking for it everywhere. So we went to all these different reactions and found it. We found it even in the ascorbic acid. Under certain conditions, we could generate this intermediate. But one of the problems that I think you're alluding to in this is that all these different techniques that I use, NMR, UV-Vis, the visible spectroscopy, and the electrochemistry, they all work best with different concentrations of K119. So it's difficult to, so that's why it's a lot of work to try to correlate all these data, because the NMR, we have to run at very high concentrations of KP119, but the absorption spectrum we have to run at much lower. So if we run in the NMR probably 30-fold excess of this amount of KP119, and that's going to give you different chemistry. So, but now that we know that that's a problem, because usually that's not a big problem. Usually it doesn't matter if you change your concentration by a factor of 2, that shouldn't have any effect at all. But the fact that we know that it does have an effect means we have to pay very careful attention to it. Yeah, Chris?
Going back to the graph of just a straight reduction, and I think everybody agrees with what you do.
These, yeah.
Yeah. And I know you may not be able to answer this question, that's just my comment. I'm just looking at other compounds and stuff. So the difference between this and like other transition metal compounds, do they all lie around the same, like if I see you have it centered on 0,
right?
Do they all lie around that, different peaks, different like lengths of like constant current, I guess?
Right, no, not at all. So so even other ruthenium compounds are not necessarily in this region.
Okay.
And so I think the fact that this reaction happens in this potential region means that that's why this particular drug seems to have some bioactivity that's interesting. And the way we adjust that, by changing the ligands that are attached to the metal, we can shift this around.
Oh.
And that's what Kepler was doing when he started doing this work. And I was doing it too at the same time, but I was doing much slower than he was. We were looking at lots of different ligands, and we were trying to see where we could optimize this particular potential. And so he was able to make this compound and patent it. I have no interest in doing that, but and it hasn't gone much further in terms of beyond the clinical trial, but that's sort of how we approached, how people in this field were approaching finding the secret sauce of the chemical.
So all these different ways you have to manipulate this compound. You see one of these ways of some of them being used to selectively target cancer cells. That secondary glutathione is overexpressed in cancer cells.
Yeah.
So is there a way in which you see targeting those specific types of cells or other types of
Exactly. So he was asking about is how can we use this information to target particular cells, and that we believe may be what we're doing. So the idea is that if we can fine-tune that reduction to happen selectively in cancer cells, but not in healthy cells, that would eliminate the side effects that happen in the peripheral platinum drug. So we basically want to turn the drug on when it's in the environment of a cancer cell. The cancer cell is slightly different chemistry than healthy cells. They tend to have lower pH on the outside. They tend to have different chemicals on the inside, like the glutathione. And so one of the things that we've been working with the yeast is trying to figure out, what environments can optimize the drugs using, and can we mimic cancer cells over healthy cells using that. So yeah, that's the end goal. All right. Well, okay.
I need one trivial question.
Okay, one trivial question.
So KP119, I don't know what KP.
Right.
119.
I'm assuming he did it on October, well, he's European, right? So 1019, right? I don't know. The 19th or some month. That's how you do your lab notes by date. I don't know how he did it. There's also a KP133 that I didn't talk about that we use as well. So the date doesn't work about it. You know. I don't know. Thank you all very much.